our maskless double-sided micro-lens arrays are cool, at least fun, to play with and to look at it. They are really efficient. This is what we are particularly proud of, because at least to our knowledge right now on the market, such numbers are probably unreachable. Hi, welcome to the Photonics4Future. My name is Dmitrii. I am a scientific researcher at Fraunhofer IOF, and today I'm going to talk about the micro-optics and how it can transform the automotive lighting in the future. And welcome, I'm really glad to talk about this topic today to you, and I'm going to share at least our vision. So, just a little overview of current automotive lighting trends. Everything needs to be compact today. We would like to save space for the passengers in the car. We would like to save construction space in the headlight, for example, or in any other luminaire in the car. And also the lighting modules today, they have to follow the design signature of the car model or of the company who is producing the car. At the same time, of course, we would like to minimize manufacturing costs. We do not want to lose money on each unit of the module. It still has to be efficient, especially if we are talking about the headlights, because in case of headlights, we still need quite enough light to be on the road ahead of us. So while being compact, we cannot lose too much of light. And this is not only applicable to the headlights, the same is for the interior lighting and for the signaling. Before I proceed with the motivation of us in this development field, I would like to remind everybody who is already familiar with this concept and explain for the new audience what kind of micro-optics we are talking about. So roughly 10 years ago, in our institute, colleagues have developed a so-called arrayed projector. It's a simple system, really compact. It consists of an LED source, in most cases white light LED, then a simple collimation lens, just a single lens, or in some cases two lenses to collimate the light, and it shines through the micro-optical component. And the micro-optical component is a double-sided micro-lens array. It has a really simple structure. Two micro-lens arrays, they stand in their mutual focal plane. And the entrance microlenses, they accept light from the main body of the system, and then they target this light through the projecting microlenses. And the projecting microlenses, they act as tiny imagers. So right behind the entrance microlenses, we have slide mask or masks, which are nothing else as openings in the form of the pattern which we would like to project somewhere on the screen or on the road, and these masks individually are imaged by each of the exit microlens. And this technology was used for the quite well-known device which is called Welcome Light Carpet and was developed together with BMW and our institute in 2015. And it's really compact. The idea is to project nice recognizable features somewhere around the car. For example, this one welcomes the driver in the car, and there is not so much of construction space underneath the car. So compactness was the killer for this killer feature for this device. And by saying it's compact, I really mean it's compact. So this is the surface of this micro-lens array which projects the pattern. So it's a little bit less than my finger. The same idea was also applied in a couple of cars for Lucid Air and for Hyundai Genesis in 2022 for the headlighting. As I said, the same idea, slight differences for the sake of the different function, but we still have the absorbing masks which act as the beam shaper. So they form the contour and the profile of the beam in the way as we need it. If there are masks, or in other way absorbing elements, there are obvious problems with that. First of all, we lose the light, so we are not being really efficient. We block most of the light cone which enters the micro-optical beam shaper. Second of all, this light gets absorbed by the masks and the heat dissipates a little bit around the component, and it can cause the unwanted element aging. And the last but not least, and actually the most important, is that to produce such component on the large scale of area, not the one which I showed to you, the small one is okay, but if we want to apply it for a headlight is much bigger. It means that the mass production gets more and more expensive because we have to apply alignment. So these two sides, or actually saying three sides, entrance microlenses, masks, and exit microlenses, they have to be really well aligned with each other. And to do it while producing that in the mass scale, each time for each unit is a little bit costly. So this is basically our motivation for the further developments. The idea is to get rid of masks, or as we say, go maskless. But we still need to do the same kind of functions for the pattern projection and for the beam shaping. And the advantages are clear. First of all, we bring up the transmission. And second of all, we potentially make the manufacturing processes a little bit simpler and less expensive. Because if there are no masks, if there is nothing in between these microlenses, then it can be a monolithic structure. So to prove to you that it's actually efficient and nice, we are going to discuss today three showcases, three different systems built on more or less the same approach with maskless micro-optics. The first one is projective turn indicator, or in other words, blinker. Second is low beam, and the final one is adaptive driving beam. So we start with the projective turn indicator, and by projective I really mean that it's a device which projects the chevrons, which indicate the direction of the turning of the car, onto the surface of the road, which can be recognized well by pedestrians and cyclists to increase a little bit the safety of the driving today. So let's assume that we still have masks and we would like to project a certain pattern on the road. For example, this cross. If we have masks, this looks like that in the front view, and you can easily see how much of area is lost. So the fill factor is less than 55%, and it's not nice, it's not efficient. Our idea is to remove masks and let the entrance microlenses act as object to be imaged or to be projected on the surface of the road or on the screen. And it means that the entrance microlenses themselves, they have to have this shape which we are going to project. For example, this cross again here. And when we tile these entrance microlenses next to each other, we can see that the fill factor, the area which acts in a useful way for us for the projection, is actually around 100%. So potentially it brings a lot of transmission in the system, and it makes our patterns on the road or on the screen much brighter. When it comes to different shapes, there are three different possibilities for such systems. The first possibility, when our desired pattern by itself already tileable, so that we can replicate this pattern on the entrance array and we will not have any dead zones, we would not have any gaps between the microlenses. This is the first and the nicest case. If we wanted to project a letter T, for example, this is a little bit more complicated because you cannot tile such a lens next to each other without any gaps. But in this case, we can decompose the pattern into elementary structures and then project them accordingly to form the final target. And the last case, which is much more difficult to realize, is when we cannot avoid these gaps between the microlenses at all. For example, if you would like to have a projector which projects a rectangle, homogeneous white rectangle, but under some angle, you have to take into account the keystone and distortion, and it means that the microlenses acting as objects, they have to be distorted in the same way. And it brings these dead zones. And to fill these dead zones with something, because we just cannot block them, there are no masks again, we decided to apply diffusive structures which would at least smear out this unuseful light around the whole projection. So it brings a little bit contrast downfall, but still keeps the system easily manufacturable and very efficient. So our case, fortunately, is with chevrons, so the first one, and let's proceed with that. So the idea in the project was to have a projector which can be installed somewhere in the headlamp of the car, or maybe where the usual blinkers are mounted, and it would project these 3 chevrons on the surface of the road. How to generate 3 chevrons only with one projector? It's pretty easy. We apply something as we call a crosstalk. So if we have a single LED under the collimator and we shine with it through the micro-optics, then we would generate 1 chevron. And if we apply 2 more off-axis LEDs, then they are being collimated by the same lens, and they shine through the micro lens arrays under oblique angle. And what happens is that each entrance microlens starts interacting not with the opposing one, but with the next or next to next one. And this generates the twins of the original chevron. And this is the function of this crosstalk, which we can utilize to make it semi-dynamic. Of course, since there are no masks, there is something which we have to consider, specifically the instant differences between the sag height jumps, the sag heights between the microlenses. You can see them clearly here, these dark lines, or slightly blurred out here. So these are the areas which we would like to block somehow, but we cannot because we don't want to use masks. And it is really important to be able to simulate and model them in a correct way, because these actually are the structures which eventually in the system bring unwanted features, stray light. And this is the realized demo. It's also not that bulky. I also have it here, so you can compare it with my hand, for example. So this is something which can be installed directly into the headlight and act as a blinker. Here you can also see a little picture of the microlenses through the microscope, and those dark lines are nothing else as the high jumps which I mentioned. And finally, to the results. This is what I was talking about. These lines we ideally do not want to have in the system, but we cannot block them, and they are originating from these high jumps between the lenslets, and sometimes we cannot do anything about it. But there are, of course, some cases and some ideas how to at least reduce this stray light, or in some cases how to completely block it. We characterized this prototype, and it was a really good result, because the brightness of the closest chevron is approximately 7 kilolux or 7,000 lux. This is something which at least 1 order of magnitude higher than the conventional projection systems with masks or GOBA projectors. And such brightness you can, for example, compare with laser projection, but laser projection, at least in automotive, is right now out of the question due to the eye safety. So we are really happy to have such results, and here you can see the blinking something like in action. So next would be the low beam. And the low beam is entirely different system. It's a combination of pattern projection, something with a specific shape, and also the shaping of the intensity of the beam. Even though it's a different system, we apply still more or less the same concept, still micro-optics, microlenses, still maskless, and there are a little bit different details in here. So our target is to have such a beam when you project the low beam perpendicularly on the screen, not on the road, but on the screen. And the idea is to have a little bit more light on the right-hand side, so you can still drive safely, and a little bit less light, and it's pointed a little bit downwards on the left-hand side to prevent the glare of the oncoming drivers. And you can see here that the target is not homogeneous, that's one thing. Then the target is really, really large, so the horizontal field of view is enormous if we compare it, for example, with the blinker. So we've designed a system which fulfills all the requirements for such a beam. It's a little bit more sophisticated. We still use one LED and now two lens collimation system. A simple sphere from the stock to collect as much as possible light from the LED, and then a custom anamorphic lens which produces this large field of view in horizontal direction, which we need because the beam is really wide, and narrow vertical field of view which later on will be shaped additionally by the maskless micro-optics. The first task in this case is to be able to accept this diverging beam by the micro-optics correctly. Since there is not so much of divergence in the vertical direction or in the side view, we can start with a really simple regular arrangement of the microlens arrays. But in the horizontal direction, from the top view, you can see that the size or the pitch of these exit microlenses is noticeably bigger. And this helps us to first accept correctly this large, wide, diverging beam from the collimator. Then there is another task, how to produce something which is not homogeneous and still without masks. With masks, it's easy. You can change the opening of the mask in each channel. For example, here it's smaller, here it's bigger, and then when they overlap in the beam with each other, you produce the arbitrary profile of the beam's intensity or brightness. But how to do it without masks? And the solution is what we call irregular Fleiser condenser. Fleiser condenser is a general arrangement of such optics. And irregular means that we start playing with the parameters of each individual channel in the system. We can change the size of each entrance microlens and its position. And we can individually steer the vertex points of each exit microlens to control each small beam from each channel individually. And this helps us to create non-homogeneous, or in other words, arbitrary intensity or brightness profiles of the beam, which is essentially needed for the low beam. And the last but not least task is to be able to produce this sharp and asymmetrical cutoff line with a kink in the middle. So let's say that we start with a simple rectangular lenslet. As you remember from blinker, the shape of the lenslet is essentially something which is projected. So if the lenslet is rectangle, then our beam will be in the shape of rectangle as well. If we start playing with the shape of the entrance lenslet, then it will be automatically repeated in the beam because it's a simple one-component imaging. But to be able to tile such entrance microlenses without any gaps, we have to repeat these structures at the other side of the microlens. And here it becomes a little bit tricky to explain. What we usually say that whatever the upper edge or lower edge of one microlens is exactly the upper or lower edge of the neighboring microlens. And the problem then is that with such arrangements, the beam would look like this step with two kinks. But in our target, there is no second kink, so it's only upstairs. And if we just let it be like that, then we are going to have something like what we call an evil twin of our kink, which is not allowed to be in the low beam. And then there is another trick, actually not final, there are much more, but anyway, how to hide this evil twin. We start to change at each channel in the micro-optics, and there are thousands of them. We start to change the position of this kink, and we realign the upper part with the exit microlenses afterwards in such a way that we still have the functional one and we don't see the non-functional one. So here we can have a little peek into the micro-optical structures. So this is the entrance array, a really small part of it, taken from the microscope objective, and you can recognize those steps of the kinks. And you can also see that the vertical extent of microlenses changes. This is for producing the vertical profile of the beam. And the exit microlenses are little bit more easy in the structure. These are just squares or rectangles, and yeah, these are not that interesting. And here you can see the picture of the module itself. I also brought it with me. So when I'm saying it's compact, I don't want to trick you, it's this. So you can just play with it, you can put it in the pockets. If you have a power bank, you can shine it as a torch if you like. This is something which we do in the exhibitions and the fairs usually. And finally, I would like to show you some optical results for the low beam. So these are two measurement pictures. These are not simulations, so we've measured that with a specially equipped special equipment, and then we just process that in the software, I guess in MATLAB, I don't remember. And here you can also see the real picture of the beam being projected at 10 meters onto the screen. So first of all, what I would like to point out, so the beam has really little amount of stray light, so the light which we don't want to have in the system. There are some lines underneath the beam which also happen due to the SAC height jumps, due to this shaped micro lenses on the entrance, but still these structures are below the beam. They can be blocked by housing and they are not going to be harmful for the driver. And what is really nice about this result is that the cutoff line is reasonably sharp. It's within the regulations of the United Nations, and it almost doesn't have any color problems. So classical headlights, even today, they have really noticeable color fringes due to the color aberrations of the optics. And since our micro lenses have really small numerical aperture, there are not so much of aberrations in the system. So this is really a nice feature that you have a neat, clean cutoff line without any color problems. So to summarize a little bit about the low beam, we were able with one of these little guys to produce 7,000 candelas on the road in the beam of the hotspot. Those who know the regulations, they will say, of course, it's not enough. That's true. But we can apply, for example, 4 such modules, and this is the photo of the final demonstrator for the low beam, which would just overlap and then produce you the sufficient amount of brightness on the road. So, for example, with 4 modules and the correctly chosen LED, we expect around 42 kilocandelas, which is even a little bit an overkill for the regulations. Sharp cutoff, no color, and the most important is the transmission of such system. It's roughly 70 to 75%, including a couple of percent of the stray light. And this is what we are particularly proud of, because at least to our knowledge, right now on the market, such numbers are probably unreachable. So even if you have not really powerful LED, and if you especially don't have much construction space, this is a perfect solution for you, because the efficiency is something which essentially brings the brightness of your beam on the road. So next would be our last case of the adaptive driving beam. And I guess most of the automotive people know what is the adaptive driving beam. It's a high beam which have switchable features. In our case, we have designed a single row driving beam, which consists of set of vertical segments which we can individually dim or switch off to prevent the glare from for the upcoming drivers or for the pedestrians on the road. And this is essentially really important because the high beam is much more brighter than the low beam. Yeah, a little bit technical details about such design. Here we are more lucky with the target, because the target is something like a vertical segment. It doesn't have any asymmetrical features, so it automatically means that our micro lenses on the entrance can be simple rectangles, and it's much easier to design and to make it work. And in this particular case, we have introduced something which we call an elementary cell. So instead of designing the whole or calculating the whole area of the high beam, which is actually quite larger than the low beam, we designed an elementary cell. It's a representation of some number of channels. In this particular case, it's 7 channels, which already built our target in a close way. And then we would just take this elementary cell, a set of 7 entrance microlenses and 7 exit microlenses, and then just repeat it within the exit area of the luminaire, just to replicate. And then it would produce as much brighter, but still the same segment. And our target was for the extent of the segment to be approximately plus minus 1 degree in the width. Obviously, the smaller the better, because then the beam becomes more and more flexible. You can switch off really, really fine features, but inevitably there are some limitations. In our case, it's a diffraction, because the extent of the segment is directly linked with the numerical aperture of the microlenses, and if we go too low, then we have noticeable diffraction, which brings down the performance. As I said, we have to produce many of such segments. In case of these systems, there are 23 vertical segments which build the whole beam. And to produce them, we apply the same concept as we used for the blinker, for the projective turn indicator. We apply crosstalk. It means that we use not only one LED on axis, we use many of them, also 23, and each of them is collimated with the same collimation optics, and each of them shines through the microlens arrays at a specific angle, which creates a set of adjacently placed vertical segments in the beam. And obviously, if we switch off a particular LED, it means that we create a certain vertical, what is called dark tunnel or adaptation tunnel or safety tunnel in the beam. And yeah, the logic is simple. Wherever you're driving, and if your car detects with the camera another car somewhere in 200 meters or maybe 100 meters, the system detects that and automatically switches off the specific LED or LEDs to darken out this area with that car. And again, purely maskless micro-optics, a little bit easier than low beam. You can still see the irregular structures of the microlenses. And in this case, the efficiency is a little bit less. It's only 40%, just because we lose the remaining 60% on the collimation optics. So the deal is the following with such micro-optical systems. The micro-optics, this double-sided irregular structure, doesn't lose much light by itself. There are still remaining Fresnel reflections, which we can decrease by applying the AR coating on both sides. But what we usually say that geometrically, there are no light losses. There is nothing which absorbs light, at least intentionally. There are no masks. And whatever the efficiency drops we have in the system, they happen on the classical part of the system, on the collimator. And just simply because we are still limited by laws of physics, the collimator has a certain étendue, so the amount of light which can go through the system, and these are the only losses which we have in the system. And here we also built a demonstrator and characterize it in our lab, but the characterization in the lab is first quite boring and also not reflecting the reality, because the high beam is supposed to work at a really long distance, more than 50 meters. And if you try to shine with such a module on the screen at 10 meters only, it looks just worse. It looks not that good as it's supposed to be and as it's going to look at the road. But we had to ensure that we are able to create sharp dark tunnels, which is true. And for example, those noticeable lines between the shining segments, these are exactly the courtesy of insufficient distance of projection. So to really test it out, we took it somewhere on the road here in Vienna, in the dark surroundings, and yeah, we pretended that we actually already have such a headlight. And you can see the demonstration of the system pretty easily. There is a pedestrian which just walks for no reason in the dark and talks on the phone, and the car detects that and switches off the specific part of the beam not to blind this person. And on the road it looks actually as it's supposed to look. To summarize, the third prototype which I wanted to show to you today, we are really compact. So I didn't bring this guy with me because it's a little bit bulkier than low beam, but our target was for the headlights always to fulfill really small vertical extent of the system. So I've mentioned that compactness and the design feature is the key for the development in the automotive lighting. And today the trend is to have these slim-like headlights which appear in the same way as the daytime running light. So we hit that target. We were still able to preserve at least 40% transmission with that, limited by laws of physics. And we can reach pretty high values of the brightness of such beams. With even one or two modules, we can reach approximately 100 kilocandelas on the road, which is way more than the regulations require. And now I would like to talk about what is essentially a concern of every automotive partner. Everybody, after I give such presentations, after we discuss such systems, after we show our demos, everybody asks, okay, that's nice, really impressive, but how can we manufacture them? And specifically manufacture with not so much of additional cost. This is really important. We manufacture them in-house, so we can produce such micro-optics purely in the institutes. The mastering is done by the grayscale lithography, more or less the same technology which is used for the production of the chips for the processors, but we apply it for the optics. And grayscale lithography helps us to achieve such arbitrary shapes of the micro lenses, like chevrons or for the low beam. And to replicate it, we apply polymer on glass molding, which is done with the mask aligner. The mask aligner is equipment which works for the micro-optics which has masks, for example, the light carpet, and we use the same equipment just to align two sides, one entrance microlens array and the exit microlens array. But since we don't have any masks, we can enable the following technologies to be applied. And for example, the injection molding. And here is where we are sure we can save some costs for the mass production. We had a project done together with our partner Optoflux, where we wanted to repeat our masters for the blinker, for the chevron-like microlenses, with the high precision injection molding. Here you can have a little hint of the tool. One of the sides is adjustable, so the idea is to perform the alignment one or several times before the mass production, fix everything, and then just do the shots and produce many of such components and to save money. The target of the project was to prove that we actually can do that with a sufficient quality. And here is the first visual hint how these micro-lens arrays look with two different ways of production. On the left-hand side is polymer on glass, our gold standard, basically the standard for the quality. And on the right-hand side is something which we would like to study, the injection molded pieces. And visually there is no difference. They look 99% the same. And fortunately, the performance is also not that far away from each other. So, for example, if we are being nerds and we would like to check all the optical parameters like the radius of curvature and the extent of single microlens, we can see that the difference between two manufacturing techniques is really, really small. So, for example, with the polymer on glass technology, we had roughly 2 or 3% deviation from the master and only 1% deviation from the injection molding. That was really a fortunate occasion. And then one more nerdy slide with a little bit more detailed characterization. We really took the 3D topography scans with the white light interferometer of such structures to analyze these regions between the microlenses, because essentially these are the most important. They bring, as you remember, most of the stray light in the beam. And we can see that these regions for two ways of manufacturing are close to each other. So the difference is only a couple of degrees in the slope of these dangerous regions. And finally, the optical comparison. So again, on the left-hand side, you can see the projection with our gold standard in the complete darkness. And on the right-hand side, you can see the same done with the injection molding technology. And obviously, there are some differences. We cannot just replicate it 100%. First of all, you can recognize a little bit of blur with injection molding because we have changed the material of the micro-optics. And in the first try, we did not take into account the sufficient change of the thickness between two microlens arrays, which essentially has to be adjusted when you change the material. But apart from that, we can see that the general behavior of the system is almost the same. A little bit more crosstalk, a little bit more stray light, but nothing which we cannot fight in the future when we put it into the industry as a future product. And then here I just wanted to prove my message that, okay, with the gold standard technology, with expensive polymer on glass, we can achieve approximately 8,000 lux for the first chevron. With injection molding, it's 6,000 or 7,000. Sounds like a big difference, but on the road, especially with some sunlight, it's not that much of a difference. The message is that it's pretty close to each other, and our conclusion was that high precision injection molding is indeed something which can help to get such structures produced in the mass scale. So, I'm ready for the conclusion. I hope I could bear a message to you that our maskless double-sided microlens arrays are cool, at least fun to play with and to look at it. They are really efficient, especially if we compare with solutions with masks applied, no matter if it's a micro-optical solution or classical solution. We can achieve something like a semi-dynamic pattern projection. We, of course, cannot be completely free with the choice of the pattern shape, but there are still some shapes which can be useful for the automotive market, like a warning sign or rectangles or something else, and we can produce them in a nice and efficient way. And we are really flexible with the profiling of the intensity or brightness of the beam, for example, low beam, when we do not want to have it homogeneous. So there is large design freedom. We can have different systems. It's not limited only to low beam, high beam, and the blinker. It can be a static high beam or something else, or warning signs, as I mentioned. To some extent, we can customize a specific system by just changing the MLA. The collimator probably can stay the same, and then you just replace one micro-optics with another. And I don't mean that you are going to have completely different function, not, but there will be some adjustment. For example, you can change European low beam to Japanese low beam, just to switch the side. And that's it, you don't have to do anything else for the system. And the modules, the luminaires themselves, they can follow, to some extent, your design preferences. They don't have to be really rectangular. They can be slightly tilted, they can be slightly deformed, they can follow the design features of the car. And there is also a possibility for the combined functionality. For example, we can, with the same module, perform a daytime running light when it's not dark. And for example, when we are then on highway in the darkness, we can switch on the high beam with the same module. So we save lots of space with that. And yeah, as I mentioned, for example, in case of low beam, we can have variations. We can switch with the functions within the modules of the low beam. For example, with one module we can create the pre-fields, and then with another module we can create the range, which is called in the industry with the kink. And finally, probably the most important for the automotive players, it enables the cost-effective mass production. So, as I said, you adjust your tool one or several times, and then you produce several hundreds of the pieces. There are clear tolerances, as in the process of the design and also in the process of manufacturing. We have studied that extensively, and basically you can imagine that many types of the automotive lights, high beam, low beam, blinker, anything else, can be produced to the biggest extent with one production line. You just change the masters, the mold structures, and you're good to go to produce new function. So that's it from my side. I thank you for the attention, and if there are any questions, please feel free to ask them now or contact us later on.
Photonics4Future. Light is the solution. Challenge limits. Shape tomorrow. Change